so what I need to introduce now is the concept of Young's modulus. Now, Young's modulus is an important concept in engineering. It lets you know how strongly you have to build something to withstand a certain force. It lets you know about how the material behaves when it starts to weaken as well. Okay, so the idea that if you were to design a cast for somebody and make sure that their bones heal correctly, then the Young's modulus would need to be taken into account. You would also need to take into account the Young's modulus of bone, and also the other thing is in terms of looking at engineering and feats of engineering in terms of bridge building, it's the idea that you need to make sure that they can withstand certain forces. So, two important equations that we've already looked at. We've already had a look at stress, tensile stress when something's being stretched, and stress is force divided by cross-sectional area. Because of that, the unit is pascals or newtons per metre squared. Okay? Strain is the ratio of the extension of an object divided by its original length, and therefore the unit does not exist. It's metres divided by metres. Young's modulus is the ratio of stress over strain. Okay, so it's how much tensile stress it takes divided by the tensile strain. Because it's pascals divided by something with no units, the unit is the same as stress. It's pascals or newtons per metre squared. When pupils calculate Young's modulus in exam, then some people get concerned because they get really large values. That's typical. Okay, so bone has Young's modulus of 14 gigapascals, which is 1.4 times 10 to the 10. And copper has got a value of 117 gigapascals, which is 1.17 times 10 to the 11. So if you're getting really big answers, that's fine. That's to be expected. There's no need to remember these answers, but it does tell you if you're going in the right direction if you're getting something of that order. Right, okay, so you could be given these individual values here and be asked to calculate the Young's modulus. In some cases, they may only give you the diameter, okay, or they may only give you the radius, and then you have to do even more, for about 4 marks. Okay, because Young's modulus is stress divided by strain, therefore, Young's modulus, which we give a capital E, is force divided by area, divided by change in length, divided by length. Because we've got force divided by area on the top, and change in length divided by length on the bottom, when we rearrange that, Young's modulus is force times by the original length, divided by the cross-sectional area, divided by the change in length. Now, please learn that. It's not on the data sheet in this format, and it's what comes up most common. It's the way it's phrased the most. Looking at this, Young's modulus is proportional to force. There's forces on the top. Young's modulus is proportional to length. Young's modulus is inversely proportional to cross-sectional area, and Young's modulus is inversely proportional to the original length. However, I've got to state not to fall into a trap. If a copper wire is 2 metres long, it's got a Young's modulus of 117 gigapascals. If a copper wire is 4 metres long, it's still got a Young's modulus of 117 gigapascals because the material is still the same. Okay? Young's modulus is a constant for a material if the limit of proportionality is not exceeded. Okay? So, you've got this direct proportional graph. The gradient would give you the Young's modulus. Okay? Thank you for listening.